Chapter 17, Equilibrium, the extent of chemical reactions. One important goal in this chapter is to develop the skills to solve equilibrium problems. If equilibrium quantities are given, we simply substitute them into the expression for K and calculate its value. For example, K is usually the product concentration divided by reactants. Sometimes you raise to a certain power. So if these concentrations are given, then you plug in and you calculate. Now, if they are pressure, then you calculate Kp. Now, however, in many times, this equilibrium concentration or pressure are not given directly. Instead, it will give you other informations. And therefore, you need to figure out how to find this equilibrium concentration, and then you calculate the Kp. And one important skill is to write reaction table and then figure out this equilibrium concentration. The reaction table shows the balanced equation, the initial quantities of the reactants and products, the changes in these quantities during the reaction, and then the equilibrium quantities. Okay, so this is a very important skill that you need to develop. Okay, and I'm going to show you an example in the next slide. Here is an example showing you how to use reaction table to solve equilibrium problems. Now we have a reaction. Carbon dioxide react with graphite forms carbon monoxide, and what is given is the CO2 is added to 0.458 atmosphere. Note that this is how much you added to the system. It's not the pressure after reaction. In other words, it's not the equilibrium pressure. Okay. Also, it tells you at equilibrium, the total pressure is 0.757. So this question does not tell you directly what is the pressure for the reactants, what is the pressure for the product, and therefore you cannot calculate Kp unless you can find out the equilibrium pressure. Okay, so here is how we write the reaction table. Okay, you write the reaction, list the reactants, CO2, graphite, list the product, clearly show the stoichiometry, which is 1, 1, 2. Okay, now in this case, we have pressure given, so we write here pressure. Now in more often, we use concentration, so moles per liter more often, but in this case, it's the pressure. And then first row, write initial pressure. Okay, again, in most of the time, it's the initial concentration, but in this case, it's the pressure. So initial pressure, and then second row, write change of the pressure, and third row, write equilibrium pressure. This is the one we need to find out. Okay, and what is given is the initial. So initial CO2. So CO2 is 0.458. Okay, now product is 0. So we add this amount of CO2. There's no CO. Okay, and we also know the total pressure, but total pressure is not in this table. So how do we find this equilibrium concentration? This important information here is the change. Okay, even though it didn't say that, but the change must obey stoichiometry. So if the change for CO2 is x, so we use x as an unknown, and we say this is how much CO2 has consumed, then the carbon dioxide must be twice of it because of the stoichiometry 1 and 2. So this is x, this is 2x, and we have a negative sign tells you CO2 is consumed. Positive sign says CO product is formed. Okay, with this information, then we can calculate the equilibrium pressure. So the equilibrium pressure is the initial, this is how much you added, you minus the change. Okay, X is the change of CO2. And product is initial 0 plus. So this is 0 plus this how much change. And that give you the final pressure for product at equilibrium. So these are the equilibrium pressure, but you may say it's not a known quantity because you still have X. And that's when you use another information, that's the total pressure. So total pressure is given. So if you add these two, that should give you the total pressure. And then you can solve X. Using this information, you solve X and then put back into the table, and then you can calculate equilibrium concentration or pressure. Okay, so next we see here. Okay, so here again, this is the table, and the total pressure is given 0.757, and this is obtained by adding equilibrium pressure of the reactants and the product, so add together. So what left is just to solve this equation using algebra. Okay, and so you have negative X, you have positive X, you combine together, so 1 negative X, 2 positive X, that give you 1 positive X. Okay, and then to solve this X, both sides you can minus 0, so minus 0.458, here minus 0.458. So this will cancel, and that give you 0.757 minus 0.458 give you 0.299. And now with this X solved, you put back into this table, and you calculate equilibrium pressure. So equilibrium CO2 is calculated to be 0.159, and equilibrium carbon monoxide is 2x. Okay, so 2 times this x solved x, and that gives you this number. And the last, we calculate the Kp is the product squared divided by reactants, and that gives you the answer. So this question shows you that we list how do we write the table. Okay, it's very important. You write the equation, all right, reactants, product, and in 3 rows: initial, all right, change, and equilibrium. Okay, so even though change doesn't tell you, but you can use a unknown, and very importantly, you should know they obey Stoic geometry according to this equation. So using those information and the total pressure, then you can calculate X and then put back into the table. Now sometimes equilibrium constant is given, and so in that case you can use product divided by reactants to equals K and solve X. So there are different conditions, but the important thing is the table format is the same. Okay, format is the same: initial, change, equilibrium, and we'll see more examples in the next few slides. Sample problem 17.6. A reaction hydrogen iodide decomposes into hydrogen and iodine. A researcher fills an evacuated 2-liter flask with 0.2 moles of hydrogen iodide. So compared to the last question, and this is not about pressure, but about the concentration. We have volume, we have number of moles, so number of moles divided by volume, and that gives you the concentration. Okay, so let's calculate the concentration. And this concentration allows the reaction to proceed at 453 degrees. So this concentration is the initial concentration you added to the container. Okay, and at equilibrium, there's another concentration, hydrogen iodide, 0.078. So this is the equilibrium concentration. This is the initial concentration. It asks you to calculate Kc. Now, we know to calculate Kc, you need to know equilibrium concentration, not only for the reactant, but also the product. And so we need to figure out these two before we can calculate Kc. So to do that, we need to write the reaction table. Here is the reaction table. Again, we have the reaction with clearly showing the stoichiometry 2, 1, 1. And in this case, it's the concentration. We have 3 rows: initial concentration, change during the reaction, and equilibrium. So what is given is the initial concentration of hydrogen iodide, which is 0.1. We just calculated using number of moles divided by volume. And hydrogen iodine concentrations are 0. We also know the equilibrium. At the equilibrium, we still have 0.078 molarity left, okay, concentration of hydrogen iodide left. So how do we figure out the equilibrium concentration for hydrogen for iodine? Okay, so again, we need to use the information of change, which obeys stoichiometry. Okay, we use an unknown and solve the unknown. So we should use x as an unknown. But which one? Should we use unknown for hydrogen iodide or hydrogen gas or iodine? Now for convenience, we choose the one with the coefficient has 1. So in this case, we can use hydrogen as x, or iodine because they are the same. Whenever you form hydrogen, you also form iodine. They have the same coefficient. So use x as hydrogen, and the iodine is also x, and the hydrogen iodide will be negative 2x. Okay, so negative 2x for hydrogen iodide. Okay, now if we choose hydrogen iodide as x, if we do that, then hydrogen should be half of it. So x divided by 2. All right, when you calculate, it's not as convenient, okay, because this is 2, this is 1. So if this is 1, this has to be half of it, okay, and that's not convenient when you calculate. So we commonly choose the coefficient 1 as x. Okay, so do that, then we can figure out the equilibrium concentration, which is the initial minus the change for the reactants. So this is the initial minus it, give you 0.1 minus 2x, and the product, it should add 0 plus x, so x and x. Okay, so now how do you figure out x? Okay, we already know at equilibrium, there's an important information is 0.078 equilibrium concentration for hydrogen iodide, and that is given. Now this table shows you it should be this value, and these two has to be the same. Okay, so 0.078 should equal to 0.1 minus 2x, and from this you can find out x. Okay, how do you do that? Okay, so let's use 0.078 equals 0.1 minus 2x. Okay, you can there are different ways to do it. So you can add 2x on both sides, for example. Okay, so you cancel this one. So now you have 2x plus 0.078 equals 0.1, and then you both sides minus 0.078 minus 0.078. So you have 2x plus 0 because this cancel, and that gives you 0.1 minus 0.078, and then you divide by 2. Both sides divide by 2, so x equals 0.1 minus 0.078. All right, so that's how you do that. That gives you this number, okay? And then you calculate the Q because you already have all the equilibrium concentration. Okay, so you can see that the information may vary, but the strategy is the same. You write the table, okay? You give X unknown for one of the reactants change, and use that information, okay? Stoichiometry, remember this is stoichiometry. You X connect to all reactants in the product, and then you find equilibrium concentration as a function of X, and then use a information to find given to find X. For example, in this case is the hydrogen iodide. Now, if you know iodide concentration, then you just use X equals the concentration that is given to find X, okay? And then you put back into the table, find all the equilibrium concentration, and then solve K. Sample problem 17.7. A chemical engineer mix two gases, methane, water, okay, in a flask 0.02 liter, so that's the volume, at 1200 Kelvin. At the equilibrium, the flask contains this number of moles of carbon monoxide, so that must be the product, and 0.084 moles of hydrogen, that's another product, and 0.045 moles of methane, so that means some methane unreacted, okay, still left. So these are the equilibrium number of moles. With this number of moles and the volume, we can calculate the equilibrium concentration. So first, let's write the equation. Okay, so we have reactants, all right, methane and water. We have products. Okay, we also can calculate the equilibrium concentration according to the information given. So for methane, okay, this is the concentration at equilibrium, and this is the concentration for product. Okay, so one concentration at equilibrium is not given. Okay, this is to be calculated. Okay, so what is the water concentration at equilibrium? Kc is given. So in this question, equilibrium constant is given. Concentration at equilibrium also given except one. We want to calculate that one. So we can write the equation. Equilibrium constant equals product divided by reactants. In this equation, carbon monoxide is calculated already, is given. Hydrogen is given. Methane is given. Water is to be calculated. So only one unknown that we can solve. So for example, if we can multiply by water concentration on both sides, the equation is still valid. By doing that, the right side water is cancelled. And then we can divide by Kc on both sides. The equation is still valid, but now the left side Kc is cancelled. So we have this equation. Water, that's what we want to calculate, equals carbon monoxide, hydrogen, methane, Kc. Everything is known here. So plug in everything, and we can calculate 0.042. So this question shows that we don't always need to use the reaction table. If we know the concentration at equilibrium, all right, and then we don't need the table. So here we know the concentration at equilibrium for almost all of them except one. We also know Kc, and so we can calculate the concentration. Sample problem 17.8. Few engineers use the chemical reaction of carbon monoxide and water to make carbon dioxide and hydrogen gas. So let's first write the reaction, all right, and balance it. So this is the balanced reaction. Reactants are carbon monoxide, water. Product are carbon dioxide and hydrogen. Now, if 0.25 moles of carbon monoxide and 0.25 moles of water are placed in a 120 milliliter flask at 900 Kelvin. So we have volume, so volume 125, number of moles of the reactants, carbon monoxide, water, are placed in the flask. That means they are initial concentration. They are not the concentration at equilibrium. So you place them in a container and let it react. The question is, what is the composition of the equilibrium mixture? So first, let's calculate initial concentration. So the concentration before reaction, that's what we add. So carbon monoxide and water both are 0.25 moles divided by volume. So that gives you 2 molarity. So we have initial concentration for carbon monoxide, for water, both are 2 molarity. And we also know Kc. Okay, we want to calculate the equilibrium concentration for all the substance, reactants, and products. So this is a typical question that it requires the reaction table. Okay, remember, we know initial concentration, we know Kc. So how do you calculate equilibrium concentration? So let's list the table. So here is the reaction table. Again, write the reaction, balance the reaction. Okay, the 3 rows: initial, change, equilibrium, and the initial concentration we already calculated to be 2 molarity for carbon monoxide and also for water. Products are 0. We also know the Kc. All right, we want to know equilibrium. To do that, we need to assume the change here is x. All of them are x. Reactants are negative, products are positive, and at equilibrium, therefore, is for reactants are initial minus the change. So 2 minus x, 2 minus x. Products are initial plus x, so it's xx. Okay, and how do you solve x? Well, we have Kc. All right, so write Kc equals product over reactants. So here product are x times x, so that's x squared divided by 2 minus x, 2 minus x, and that gives you this equation. So how do you solve this equation for x? Well, usually it's a quadratic equation, so we need to rewrite as a quadratic equation. But in this case, there's a simpler method because on the right side, both are squared. So a simple way is to square root all of them. If you square root this, the left side, you need to also square root it. And so what you get now is square root Kc, which is 1.56, that is given, equals the right side after you square root of the square, and that gives you x divided by 2 minus x. Okay, so this is a quite special case. Now usually you cannot square root, because for example, if x squared divided by 2 minus x, then square root doesn't work unless both numerator denominator are square root. Okay, in this case you can do that. So how do you solve x for this one? All right, so there are many ways. Again, so one way is you multiply 2 minus x on both sides. So you just want to remove the denominator. So you get, so that cancel each other. And then you calculate this one and plug in, and then you remove the number on the right side. So what you get is x equals 1.11. Okay, so square root 1.56 is 1.25. Okay, so what you have is 1.25 times 2 minus x equals x. All right, and so this will be 2.5 minus 1.25x equals x. Okay, and then you both sides plus 1.25, so that gives you 2.5 equals 1.25 x plus x, and that gives you 2.25x, and therefore you can solve x. So both sides divide by 2.25, 2.25, and x equals 1.111. All right, with x solved, plug in this table. Okay, and then you have all of the equilibrium concentrations. Okay, and so for the reactants 0.89, products 1.11. Sample problem 17.9. Phosgene, which is COCl2, decompose into CO and chlorine. This reaction has a Kc 8.3 times 10 to the minus 4. We want to calculate the concentration of product Cl2 and the reactants phosgene when the following amount of the reactants decompose in a 10-liter flask. So this is the volume, and this is the number of moles of the reactants added to the container or the flask, and we want to calculate equilibrium concentration. So again, just like last time, okay, we can calculate initial concentration. So initial concentration is the number of moles reactant divided by volume. So that's the initial concentration. To calculate equilibrium concentration with Kc, we need the reaction table. So at this point, you should be familiar with writing the reaction table, right? So first write the equation, balance, and 3 rows again: initial, change, equilibrium. And now initial concentration is calculated 0.500 for the products. So how do you calculate equilibrium? Okay, and you assume one of the substance change is x, since the coefficients are all 1, and therefore they are all the same. Reactant is negative, product is positive. Okay, and then equilibrium concentration should be reactants is the initial minus change, product is initial plus x. Okay, so at this point you should be very familiar with this now. So how do you solve this one? Okay, you write the equation Kc equals product divided by reactants. All right, so product is x times x, so it's x squared. Reactants 0.5 minus x, and Kc is given. So compare with last question, you can see here this one doesn't have a square, so square root on both sides does not work. Okay, and therefore we need to use quadratic equation. So next we're going to show you in general how to solve this kind of question. Here is the equation again. Kc, which is 8.3 times 10 to the minus 4, equals x squared divided by 0.5 minus x, and we want to solve this x. Before we use the quadratic formula, as we will do later, but first let me introduce a trick that turns out to be very useful. Note that Kc, 10 to the minus 4, that's a very small number. Kc is the equilibrium constant, which measures how far reaction goes to the right, to the product. If equilibrium constant is a small number, okay, that means the reaction does not go far significantly to the right, to the product. So the change x, which is how much reactants forms product, should be a small number. So if Kc is very small, reaction does not proceed far to the right, then sometimes x can be neglected. Okay, so let's think about a number. Okay, let's say number 2. Is number 2 a large number or a small number? Well, that depends on what number you are comparing with. For example, If you compare with 10,000, okay, you use 10,000 minus 2, well, then we can say, well, that is just about 10,000. You can omit 2 because 2 is very small compared to 10,000. All right, so it doesn't make much change. On the other hand, if you use 3 minus 2, then you cannot say, oh, this is approximately 3. You omit 2. That doesn't make sense because 2, 3 are comparable. So if you compare with a big number, then the small number can be omitted. All right. So in this case, because KC is a very small, we assume X is much smaller compared with 0.5, and therefore the equation becomes x squared divided by 0.5, okay, instead of 0.5 minus x. All right. Now you may ask, can we omit x squared? Well, no, because we are not comparing with anything. For example, if we have a number 2, you cannot say, oh, omit 2. It doesn't make sense unless you compare with 10,000 or 1 million. Okay, 1 million plus 2 or minus 2 doesn't make much difference, just 1 million. So here, 0.5 minus x, we can just write 0.5. But x squared, you should keep it. All right, and that make the solution much simpler because now you can simply multiply 0.5 on both sides, 0.5 on both sides, so that you cancel 0.5 and you get x squared equals 8.3 times 10 to the minus 4 times 0.5, and x should be square root of this. So you immediately solve x, okay, to be 2 times 10 to the minus 2, and then plug in. You can calculate at equilibrium the reactant is still 0.48 molarity left, and the product 2 times 10 to the minus 2. Okay, so after you solve everything, you should check your assumption. Is assumption right? We assume x is very small, that can be neglected. But is this assumption right? So we calculate, okay, x, okay, divided by the concentration, which is 0.5. We compare it and see what is the percent of the change. It turns out to be 4%, which is much smaller than 5%. So if the change is less than 5% of the concentration, then we can say this is a small number. Our assumption is right. So this is correct. Okay, and so in this case, question A, okay, the added concentration is the number of moles is 5 moles, so that the concentration is 0.5. So in this case, X is small, that can be negligible. What if we add a small number? Okay, in B, 0.5, the concentration will be a small number. So is X is still so small that it can be negligible? Okay, we'll see in the next slide. In question B, the added number of moles for reactant is 0.1 mole. So the initial concentration should be 0.1 divided by 10. That gives you 0.01 molarity. And then we write Kc equals product divided by reactant, which is x squared divided by 0.1 minus x. So this, instead of 0.5 as the last question, here is 0.01 and equals Kc. Okay, and if we also assume x is so small that it can be negligible, because Kc is small, so x is small, and then we can have a simplified equation. And so Kc equals x squared divided by 0.01, and just like last question, we multiply 0.01 here, multiply 0.01, and so this cancel each other, and you get x squared equals 8.3 times 10 to the minus 4 times 0.01, and therefore x should square root of this one, and you get x equals 2.9 times 10 to the minus 3. So we solve the x, and we put back into the table to solve equilibrium concentration. But is this assumption right in this case? We need to conform it. So we calculate a percent change. So the percent change is x divided by concentration. In this case is 0.01. That gives you 29%, much greater than 5%. So this change is not small, and therefore our assumption is not justified. So in this case, we cannot use this assumption. So you can see here the trick to omit x, because x is small, is very useful in some cases, but not always useful. Okay, the assumption is useful when two conditions are valid. One, Kc is very small, so x is small, but not that's not enough. The concentration that you are comparing with must be large so that you can omit x. So two things. One, this is small. One, two, the concentration of the reactant must be a small number. Okay, this is small. Oh, sorry, this is a large number. Kc is small. R, reactant's concentration, is large. Then you can use the trick that x is so small, omit it, and then therefore you can solve the equation easily. But what if one reactant's concentration is small, as this case? How do we solve it? Okay, we have to use quadratic formula. We'll see in the next slide. Here is the equation we want to solve. So x squared divided by 0.01 minus x equals 8.3 times 10 to the minus 4. And we cannot omit x because this concentration is not a large number. So how do we do that? Well, first we multiply by this denominator on both sides. So 0.01 minus x, 0.01 minus x. All right, so left side, this denominator is cancelled, so you have x squared. The right side is 8.3 times 10 to the minus 4 times 0.01 minus x. Then you expand it, so this number times this one, and then times this one, so you get 8.3 times 10 to the minus 4, 6, because minus 4 and times 0.01 give you minus 6, minus 8.3 times 10 to the minus 4 times x. Okay, so note that we still have x, and that's why we have to use quadratic formula. We'll see. All right, so let's move all these terms into one side, for example to the left side. To move this to the left side, you should change sign, so you have x squared plus 8.3 times 10 to the minus 4x, and positive becomes negative 8.3 times 10 to the minus 6, and the right side becomes 0. So this is a quadratic equation. The general form for quadratic equation is ax squared plus bx plus c equals 0. A is the coefficient in front of x squared. In this case is 1. So this is 1. A is 1. And b is the coefficient in front of x. And so that in this case is 8.3 times 10 to the minus 4. And c is this number, which is negative 8.3 times 10 to the minus 6. For a quadratic equation like this one, the general solution is called the quadratic formula, which is 2a negative b plus minus square root b squared minus 4ac. So now all you need to do is plug in a, b, c, you get the solution. All right, so in this case, so it should equals to 2a, so just 2 because a is 1. B is 8.3 times 10 to the minus 4, all right, positive, negative, square root, 8.3 times 10 to the minus 4 squared, minus 4 times a, okay, so let me because the space too small. Let's move here. So should square root b squared is 8.3 times 10 to the minus 4 squared minus 4 times a, in this case is 1, times c is negative 8.3 times 10 to the minus 6. Okay, so that's the square root here. So plugging everything, use your calculator, you should get two solutions, because you have positive, that give you one solution, and you have negative, give you another solution. So you should have x1, x2, but only one makes sense. You will see that. And in this case, the solution give you 2.5 times 10 to the minus 3. The other one is 0.01. Oh, sorry. It's this. The correct solution is 2.5 times 10 to the minus 3, and therefore the 0.01 minus x give you this. That's the concentration for reactants, how much left. Okay, so this is the solution. All right, and you calculate the product CO is 2.5 times 10 to the minus 3. So quadratic formula, okay, is the general way to solve equilibrium problems, but most people find these steps time-consuming. So most people will prefer using the assumption that we can omit x whenever possible. For example, whenever Kc is a very small number, and this is not a small number. So if this is a large number, this is a small number, then people will prefer use the other way. Just omit x, makes solution much simpler. But if the concentration is not so small, or Kc is not a small number, or concentration is not a large number, then you have to go through this all these steps, the quadratic formula, to solve the solution. We have seen that the assumption x is a very small number can be neglected, is very useful, but only valid when two things are met. One is the equilibrium constant is small, very small, and the initial concentration is relatively large. Okay, so two things. But how do you know before you calculate? All right, so you use this large number divided by this one. If the ratio is greater than 400, then the assumption should be right. However, if this initial concentration is not large enough, so when you divide by Kc, it's smaller than 400, then assumption is not right. So you cannot use that assumption to omit x. Sample problem 17.10. This question is about a reaction between methane, hydrogen sulfide to form carbon disulfide and hydrogen gas. In one experiment, we mix the reactants and the product in the vessel. 1 mole methane, 2 moles hydrogen disulfide, 1 mole carbon disulfide, and hydrogen gas 2 moles. All right, and the volume is 250 milliliter, and the question is, in which direction will the reaction proceed to reach equilibrium? So notice that these are the number of moles you mixed before the reaction. With the volume, you can calculate initial concentration for the reactants and the products. So when you mix reactants product in a system, so the reaction, if this is reactants and this is a product, okay, so depends on how much reactants and the product in the system, the reaction may go forward. Okay, more reactants produce product, or the product will go back to reactants. Depends on how much you have in the system. How do you predict the reaction direction? Okay, one way you already learned is to compare the reaction quotient and the equilibrium constant. If Q is less than K, that means in the system the reaction has the system has a very large amount of reactants, small amount of product, because Q equals product divided by reactants. So if Q is small, that means small amount of product, lot of reactants. So the reaction will go forward to produce more product until Q becomes K. When Q becomes K, then reaction reach equilibrium, and there will there's no net reaction anymore. Okay, so when Q is less than K, reaction will proceed to the right side to produce more product. If Q equals K, then reaction already reached equilibrium, no net reaction. If Q is greater than K, then according to this equation, the system has too much product, and so the reaction will go reverse, left side. So it will go left to consume product to increase reactants until again Q becomes K. So until Q equals K, then it reaches equilibrium. Okay, so to calculate the Q, we need to know the concentration. All right, so calculate the concentration, we use number of moles divided by volume. These are the initial concentration. So this is for methane, and we calculate concentration for carbon, hydrogen sulfide, carbon dioxide, and disulfide, and hydrogen gas. With this concentration, we can calculate the Q at the beginning. So this is the initial Q, which is 64. Okay, don't forget raised to power. All right, in the equation you have a 2 and a 4. So compare this Q and K. We can see that Q is much greater than K. So that means the system has too much product, and therefore the reaction must go reverse to the left side to reduce product to increase reactants until until Q becomes K, then reaction reach equilibrium. Okay, so A is a question that we learned in the beginning. So now let's look at the B. Okay, in B we know that at equilibrium methane concentration is 5.56. So we have the initial concentration. These are the initial concentration. We also know at equilibrium one concentration, okay, for the substance. The question is, what are the equilibrium concentration for other substance? Okay, so this is a typical kind of question, requires the reaction table. All right, so you need to assume the change is X, and then using this information, the Kc is 0.036, we can solve X, the unknown, and then calculate equilibrium concentration. So please pause the video, try it, and see if you can calculate equilibrium concentration. Here is how we do it. First, you write the balanced reaction, and 3 rows: initial concentration, concentration change, equilibrium concentration, and then put the initial concentration into the table. Okay, assume one substance change is X. For example, methane change is X. Then carbon sulfide, disulfide will be also X. Hydrogen sulfide will be 2X. Hydrogen gas will be 4X. All right. And note that on the right side, these are negative. We'll put a negative sign here. And this is because in question A, we already find out the reaction goes reverse. Okay, because Q is greater than K. So it will go reverse to the left side. That means these are actually reactants, all right, in this system. So if they are the reactants, they will be consumed. So they'll become smaller. And so we put a negative sign here and positive sign. These will be formed, will increase. All right. And therefore, at equilibrium, so the left side will be 4 plus X. Because they are formed, they will increase. You add X, you add 2X. On the right side, because they are consumed, and therefore you minus X, minus 4X. Okay. Now, as you learned before, usually you will use K equals product divided by reactants, that will usually lead to the quadratic equation. So solution will be time consuming. But in this case, what is given is one of the concentration at equilibrium. So here the table tells us methane at equilibrium should be 4 plus X, and here tells you should be 5.56, and therefore we know 4 plus X from this table should equal to 5.56. That immediately give you solution X equals 1.56. All right, so this is much simpler than when you use K. So if you don't have the equilibrium concentration at all, then you may need a quadratic equation. Okay, that will be time consuming to solve it. But if we know one of the concentration at the equilibrium, then simply use this equation, use this concentration equals the one from the table with one unknown. That gives you a linear equation. The solution is much simpler. Okay, so with this X, we can calculate. So put back into the table. Okay, put back, and you can calculate all the equilibrium concentrations. Let's go over the steps in solving equilibrium problems. The key step is to construct a reaction table. To do that, you need to first write the balanced equation, and then you write 3 rows: the initial concentration, the change, and the equilibrium. Now sometimes you have a mixture, reactants, products, and you don't know whether reaction go forward or reverse. In that case, you need to calculate Q. Compare with K. From this information, you can determine the sign of X. To solve X, usually we need a quadratic formula. Now, but sometimes we can simplify the math by assuming X is a small number, which is negligible. So in that case, the initial concentration minus X is approximately just the concentration itself. So that will simplify math. And this is valid when the K is a small number and initial concentration is a relatively large number. So in that case, you can make this assumption. And in the later chapters, you will find that when we solve weak acid, weak base, in that case, the acid constant is a small number, and this strategy turns out to be very useful. Okay, so after you solve X, you need to confirm the assumption is justified. You can calculate X over initial concentration and see if the percent change is less than 5%, and then you can confirm it is justified. Otherwise, you have to use quadratic formula to solve it. All right, and then after X is solved, then you find the equilibrium quantity for all the substance. The skills to solve equilibrium problem is very important. So please practice and try all these follow-up questions, and practice as much as you can. Please read the textbook up to sample problem 17.10. In 8th edition, it's page 769. Go over my lecture notes, practice, work on the follow-up problems.